If you've not heard of electric plasma jet engines, it's all the rage right now in the world of automobile engineering. Apparently, a group of genius scientists think we can build more modern airliners with engines that run exclusively on clean energy and fresh air. If successful, this would be a big win for mankind, as it would be bye-bye fossil fuel and hello cleaner, greener Earth. But just how feasible is this vision, or are these guys just building castles in the air? In today's video, we are going to be test flying the electric plasma jet engine, metaphorically of course. By the time we're done with this video, you can let us know what you think in the comment section. But before we go into the exciting world of electric plasma jet engines, let's go under the hood of regular jet engines first to see how they work. This way we can appreciate what changes plasma jet engines are attempting to bring to the table. First things first, jet engines run on jet fuel, which is a mixture of kerosene and petroleum. When the engine is fired, jet fuel mixes with compressed air and then gets ignited. When this happens, gas is released, and the gas, after being heated rapidly, quickly expands and then explodes. The force of the explosion is what powers the fans, or sometimes it's just directly blasted through the back of the engine, what we know as classic jet thrust. In contrast, electric plasma jet engines avoid the whole hydrocarbons issue altogether, which are smelly and toxic anyway. Instead, these engines create that much-needed gas expansion using hot plasma. If you didn't already know, plasma is a state of matter like solid, liquid, and gas. Plasma requires specific conditions in order to exist. So, for instance, you can find plasma at the center of a burning star, or you can find it in the air around certain highly charged phenomena. A good example of such phenomena is a lightning bolt. Now, if there's a way to superheat plasma artificially, then the resulting expansion should be able to power a jet engine with enough thrust to fly the aircraft, at least in theory. The premise has been tested in certain labs in Berlin, as well as in the United States. However, the breakthrough came out the most unlikely of places halfway around the world, from either of the aforementioned places. Wuhan, China. Yes, the very same Wuhan, China. Professor Hua Tang is a polymath with laudable works in a wide range of fields ranging from artificial photosynthesis to nanotechnology. One day he was experimenting with how microwaves could be applied in the synthetic production of diamonds. Suddenly, Tang got an epiphany. Maybe the technology he was experimenting with might just be able to generate thrust. He got to work immediately, and with the help of his team from the Institute of Technological Sciences at Wuhan University, designed a special device. This device worked by ionizing compressed air by passing it through electrodes, and then forcefully passing the compressed air through a quartz tube. The result was plasma, but at a low temperature. But here's the clever thing about this work. Now, the plasma we just talked about is kept in this special tube that intersects with a waveguide, which is more or less a pipe that carries magnetron-generated microwaves. As this tube gets closer to the quartz tube, it narrows increasingly such that by the time the low-temperature plasma and the microwave meet, the plasma is at its narrowest point, and the microwaves are at their highest intensity. When the two eventually meet, the by now intense microwaves energize the particles of the plasma so they oscillate widely. This wild oscillation then triggers a release of energy along with a great deal of heat, about 1,000 degrees Celsius. And guess what this produces? You guessed it, the thrust we've all been searching for. Right now, this innovation is still in its early developmental stages, but Tang is quite optimistic about the future of his innovation. He believes that would only be a couple of years before his invention starts powering drones, and then shortly after it would progress to powering whole aircrafts. With this electric plasma jet engines underway, therefore, can we forget about oil now? Well, not yet. There are still a couple of nicks Tang and his team need to straighten out. For instance, that 1,000-degree heat released isn't exactly a cozy temperature that aviation-grade engine housing can endure. It's much too hot. Hayden even. If we went ahead anyway and applied this solution to jet engines as we know it, it would most likely lead to plasma erosion, which is quite deadly. Of course, we also talk about scale. In the laboratory, Tang's invention lifted a 1-kilogram steel ball over a tube of 24 millimeters in diameter. Now, hypothetically, this simple force is quite scalable to the point where it powers a jet engine. However, for that to happen, we'd also have to scale up airflow by a factor of roughly 15,000. Besides, when it comes to engineering, it rarely ever happens that something that works on a small scale goes on to work the same way at a much greater dimensions, like that of a jet airliner, for example. But there are yet bigger issues like how the engine is supposed to be powered mid-flight, since the jet wouldn't be able to access the power grid while on its journey. For all the challenges with jet fuel, we at least know the batteries are able to somehow manage at that same weight. With the electric plasma jet engine, we need about 43 times more energy, and we all know how important weight is when going airborne. In Chang's experiment, a total power output of 28 newtons of thrust per kilowatt was generated. Of course, this figure does not mean much standing alone, so let's give you perspective. The Airbus A320 generates roughly 220,000 newtons of thrust. What this means, therefore, is that if we are to power reasonably rooming aircraft like the Airbus A320 with Chang's engine model, we would need to burn over 7,800 kilowatt of power. If we are going to use the current battery technology to generate that power, then you're looking at almost 600 Tesla Powerwall 2 units, and that's just for 1 hour flight. This isn't even that helpful, especially when you consider that the Airbus A320 can only carry about 200 Powerwall units as payload. So, like many other researchers in the field, Chang is hoping for better batteries so he can get his invention up and running. There's the option of working with compact fusion nuclear reactors like the Russian KLT-40s, for instance. But the idea is unlikely to work since there's no way to shield the passengers from the radioactive waves. And we haven't even factored in the catastrophe that would be unleashed should the aircraft suffer a crash. And still on the power issue, it's been pointed out that even if somehow we were able to harness all the power needed on a plane, the cabling we need to carry all that power to the plasma engines would be unbelievably heavy, at least with where we're at in terms of technology. The team of scientists at Wuhan have made lofty claims, but many analysts do not share their ambition and optimism, as they believe the proposed technology has many inherent flaws, even if we were able to somehow resolve the power issue. When asked, MIT professor of aerospace engineering Stephen Barrett said, "This is wrong in terms of the physics and measurements. What they've essentially done is like heating a stove top pressure cooker until the valve rattles and calls the result thrust. But pressure cookers don't fly." In his opinion, the only way adding heat is going to work is if you compress the air first, just like in a jet engine. But this would require massive amounts of power. This is the reason jet engines use compressors. Else, as Barrett puts it, you could just ignite a candle and get thrust. But hold on, don't toss the technology out just yet. NASA might have something to say to us that might be helpful. For a few years now, NASA has been using electric plasma engines in its rockets. But of course, they use these engines in space, where spaceships don't have to contend with the friction that comes from atmospheric pressure. Hence, rocket engines work perfectly, simply energizing exon plasma. There's actually only a very little thrust generated, but these guys have had years constantly accelerating in space, so attaining the high speed they need to complete their interplanetary missions is no longer a challenge. If what the futurists say is anything to go by, though, we can look forward to hybrid engines in the near future. The plasma jets would be used for cruising when at high altitudes, while the fossil fuels would do the heavy lifting required for takeoff. Still, as you can probably tell, the amazing green technology that is the electric plasma jet engine wouldn't be clear for takeoff anytime soon. A lot of work still needs to be done, and that would require some time and patience. So what do you think about electric plasma jet engines? Let us know your thoughts in the comments, and don't forget to like this video and subscribe to Top Quick Peek for more amazing tech-related content.